I'm Joe Greathouse from AMD Research, and I just want to point out that this work was done in conjunction with Bo Su from the National University of Defense Technology in China while he was a co-op at AMD Research. So I want to start this talk with a question. So why isn't my thing working? That's a terrible question. How fast does your application run at different frequencies? What happens to the performance of your application when you change DVFS states? So for instance, if you double the frequency of your core, does your application get twice as fast, or is it limited by something else? So the last talk went into a lot of details about this. Really good talk, by the way. And so this is kind of digging even deeper into one very fine section of that talk. But I think more people care about this than you think because, for instance, how's your application affected by the frequency governor in your kernel? Or what does the firmware on your processor do whenever it changes frequency? How does it affect your application? And so really the essential question I'm trying to answer here is that if you know your performance at one frequency, what's your performance at a different frequency? And I'm going to try to discuss a way to do this on existing hardware because it's a little bit harder than you may think. So in general, let's just illustrate what happens whenever you change the performance or the frequency on your core. So on the x-axis here, I'm showing frequency, and the y-axis is some performance. All of this is normalized to the bottom left-hand point. And so if we ask the question, how does an application's performance scale? Well, one potentially pessimistic answer is that it doesn't. So you change your frequency, you move it all over the place, and absolutely nothing happens to your application. That's relatively rare, though. So maybe a more optimistic estimation is that your performance scales exactly with frequency. You double frequency, you double performance. Great, everybody wins. Well, that does work for some applications, computationally bound applications like bzip2 in the spec suite. When you spend most of your time in the core, more core frequency is better. But that's not the case for all applications. And so I'd posit that a lot of applications lie somewhere here in the middle, something in between these 2 points. And so, for example, in the spec suite, mil-C looks like this, where you double frequency and you get about 50% more performance. The error bars I'm showing here, though, are kind of big, right? You lie somewhere between perfect scaling and no scaling at all, which is not a really great answer to give. So let's start by asking a different question. Why aren't we on that top line where we get perfect scaling with this application? And so this is an illustration of how something like bzip2 may look, where the vast majority of its time is spent grinding away on compression algorithms in the core, hitting in the cache, and all the work it does is in the core's clock domain. And so when that's the case, if you change the amount of work you do per second in that core clock domain, then the amount of time it takes to run the application scales with frequency. So you run faster, it takes less time. But what about applications that didn't scale 100% with frequency? Well, in that case, this is just an illustration of something you may see there. So in this case, there are definitely times when you are working inside the core, when speeding up the core clock domain does help your application. And that's why an application like mil-C does benefit from added frequency. However, I've added some extra bars here. So these orange bars are, in fact, time spent in the core waiting for data to return from memory, which can take hundreds of cycles when you may not have any work to do. And memory is in its own clock domain, which means that if you change the frequency of what happens in the core, it does not affect these orange bars at all. And so what that means is that both time in the core and time in memory is important whenever you're wanting to estimate frequency performance differences. Now, to make sure everybody's on the same page, I'm ignoring I/O in this talk, which is important, absolutely. But I'm mostly looking at what hardware affects here. And so I think you can measure things like I/O time spent waiting on hard disks, et cetera, in software or the operating system. But measuring this memory time is the question I want to talk about here. And so how do you estimate memory time? It's a little bit harder than you think because modern microarchitectures make this difficult. So, well, first of all, we don't really have a whole lot of great performance counters in hardware. We give what we can, but towards that, a lot of people are using what counters they can find to make estimates like this. An example of how to estimate memory time is all cycles that you have a load outstanding in the system. Maybe that's the amount of time that your processor stalls. A different one may be that your memory time is related to the number of cache misses you have. That's the number of times when you go out to memory. But modern out-of-order microarchitectures make these inadequate for estimating the amount of time that you're stalled on memory. Let me illustrate an example of this. So in a modern core, maybe you run some application here, and you spend some amount of time working in the CPU, and then eventually you stall on memory. This is what I showed before. But the difficulty that modern out-of-order microarchitectures allow is that you can continue to do work after one of these accesses to memory leaves the core. And in fact, that extra work can send more parallel accesses to the memory system. And so these multiple parallel accesses are one of the reasons why you can't just count cache misses. These three take place in parallel here, but they may take place serially in some other application, meaning 3 misses to the cache are not the same in different applications. You'll notice that the core does stall here eventually. It runs out of work to do under this miss. Eventually, some data comes back, and the core starts working again. Now, one of the things I've illustrated here is that you can have computation overlapped with memory accesses. And so what that means is that even though you have some amount of time where you have data outstanding to the memory system, increasing the core frequency will still help that second purple bar, even though part of it is overlapped with memory. So that's another difficulty of using one of these 2 bullet points I mentioned up here. And a third thing to note is that accesses to DRAM take variable amounts of time depending on open page policies, hits in row buffers, and lots of other complex things deep in your hardware. And so it's really pretty difficult to estimate memory time in a modern core. So a number of research groups over the last few years looked into this, and there were 3 groups in particular that about a year apart from each other all told, all came up with the same answer, and we're going to call that a leading load system. And I want to describe what that is because they all came up with pretty much the same answer and believe it to be pretty good. So a leading load system, this is the same example I showed before, but in a leading load system, the first non-prefetch load that leaves the core clock domain is considered a leading load. And so in other words, for instance, this access right here is the first one to leave the core. Any other accesses that take place while a leading load exists are not leading loads, meaning that these 2 here are not leading loads because they are memory level parallelism. However, when this first leading load completes, then the next load that takes place that leaves the core is also a leading load. That's just a definition of what that means, and the important point of this model is that they estimate that leading load time, the amount of time that any leading load is outstanding in the system, is equal to memory time. And so this is the time that does not scale with core frequency whenever you're making an estimate of performance. And they showed this, all 3 of these groups ran simulations of this because they didn't believe it existed in real hardware, so they ran it through each independent simulators and saw that over a 2x change in frequency, this gave them the ability to estimate performance with about a 0.2% error all told. And so their takeaway from this is that hardware companies should add leading load counters in so that people can make good DVFS decisions. Well, good news then, because you can approximate leading loads performance counters on existing AMD hardware going back to about 2007, kind of by happenstance. So on AMD processors, CPU cores in their first 2 levels of cache share a clock domain. That's what we show over here on the left of this screen. And any time that you change the core, it changes all the performance there so that whenever you increase frequency, any computation that happens in the core or memory accesses that hit in the L1 or L2 all increase performance. Now, when you miss in a request to the L2, you send a request out to the L3 cache if it exists and the DRAM system. And these requests, there can be lots of them in parallel and they can return out of order. So you have to hold the status of these misses in some type of hardware structure. And that's what we call misaddress buffers or MABs. And in the literature, they're commonly known as misstatus handling registers. Now, in AMD processors, these MABs are allocated with a fixed priority. So what that means is the first one that is open, that is the highest priority, is the one that will hold the miss. So for example, your first miss goes into MAB 0. In our most current processors, the lower number of your MAB, the higher its priority. So the first miss goes into MAB 0, and it goes out to the DRAM system to eventually return. If your next miss takes place before it returns, you need to put it somewhere, so you put it into the next highest priority MAB, MAB 1, and so on and so forth. Eventually, the data returns from the memory system, and let's say it returns for the entry or the load that came from MAB 0, and you clear out that MAB, send the data to the pipeline, and move on with your life. However, if the next load comes in from the L2 cache here, we see that it goes into MAB 0, even though potentially MABs 3 through N are all open. And that last bit is important because that's essentially the definition of a leading load. Entries go into MAB 0 or they are leading loads, if no other MAB 0 entry or leading load already exists. And so if we can count the amount of time that you have a load outstanding in MAB 0, you can count the time that a leading load exists in these systems. And again, good luck. We have performance counters to do this. So the performance event 69H in our last 2 generations of processors allows you to count the number of core clock cycles that there is an event outstanding in MAB 0. And so what that means is that we can build up a leading load estimation model based off of this MAB. So essentially, you count the amount of time that there is something in MAB 0, and you count the number of cycles, you divide by known frequency, and that gives you the amount of time that you have a leading load outstanding. That amount of time does not change when you change core frequency, but all remaining time in your application does. That's essentially what these equations here are saying. Now, we'd like to evaluate this somehow, and so the easy way to do that is to run the application at one frequency, estimate how it will run at another, and compare by running it at that second frequency for real. And the difference between what you estimate and what you see is an estimation error. Lower is better. So we ran against not just this LL-MAB model I described in the previous slide, but also against the simple linear model, which assumes that all applications scale perfectly like bzip2. This is also sometimes called a constant IPC model. And we also compared against a work from IGCC 2011 called Green Governors. The paper is named the same. And in this case, what these folks did was they counted the number of L3 cache misses, assigned each of those misses a certain amount of memory time, and then calculated the whole program's memory time by just adding all of them together. Now, how much time you add per miss is, you have to train to do that. And so rather than training against a known set, what we did was we picked this delay time to minimize error in this model. So we gave them the best benefit of the doubt we could by essentially testing on our training set for this Green Governors model. We ran all of this on an AMD OpteronTM4386 processor, which is a second generation family 15H core, also known as pile driver. We've run this on a couple others, including an old Phenom 2 core, which I don't want to show here because this is a short talk and I'm already running low on time. We ran this on Fedora 19. We ran 66 single-threaded benchmarks, and whenever we ran them, we would lock them to one core using NUMA control. And then using MSR tools, we were able to read these performance counter registers around running the application. The minimum frequency that this core can run at is 1.4 gigahertz, and the maximum user accessible frequency is 3.1. So those are the 2 we use to run these tests. And so this is the estimation error that we see in these applications over these benchmark suites. So the 3 bars you see here are the linear estimation model, the Green Governor model, and finally this LL-MAB model that we built. And again, lower is better here because that means you are closer to getting the correct estimate of how your performance will be when you measure at 3.1 gigahertz and estimate how the application will run at 1.4. And so we see here that LL-MAB model is better, but it's not as good as the simulation would have told you. So the simulated estimates were that this model would be about 0.2% error, and we're at about 2.5% error. And that's differences in the fact that the MABs don't just hold demand misses, they also hold prefetch misses. The simulations all ran with constant memory latency, and real memory latency is different. So it's a mix of not having a perfect leading load counter and the leading load simulations being a bit optimistic. And finally, I wanted to move over to standard deviation. And that's because when you're making an estimation of performance, yes, it's good to have a low error, but I also argue that it's bad to get it right sometimes and get it terribly wrong in others. And so this is essentially the variance in estimation error, and showing that not only do we get better estimates, all told, our estimates are better, but that we also are more consistent with our estimates. The error of our estimates. And since this is a short talk, I think I'm just about at the end of my time, so I'll go ahead and put this up here to make AMD Legal happy and ask for any questions.
Xiaosong from QCRI. Very interesting work. I'm just curious, you did the evaluation with frequency 1 and then frequency 2. Is frequency 2 higher or lower, or did you test both cases?
We tested both cases. I believe we didn't have room in the paper, or I didn't have time in the slides to show both cases. Going down in frequency was a little bit more accurate. I showed 2.5% error here because you want to put your best face forward. It's about a 3% error going from 1.4 up to 3.7. And just for reference, in all cases, we disabled the boosting to higher frequencies that are available on these cores, the ones that the hardware does automatically.
Thank you.
Hi, Jason Mars, University of Michigan. Good talk. I think it's a really nice contribution you made here, very clever. But I'm curious as to what could you do on an Intel architecture to try to approximate?
An excellent question that I did not answer when the reviewers asked it, because I'm not paid to do that. No, so really, there are other works looking at estimating DVFS performance on all kinds of architectures. And in fact, there are works that build up regression models based on lots of performance counters, which essentially helps even out the fact that you might have the perfect one single counter to do everything. And so for instance, Barry Roundtree had a paper, his leading loads paper from IGCC 2011 showed that you could build up a regression model on Intel processors that would get about this error rate, but it took 4 to 6 counters to do that. I did look through the Intel manuals and I didn't see something like this. I spent about a day wanting to be fair, but there are definitely mixes of counters that you can add in to do this. One of the benefits we feel about this is that it only takes either 1 or 2 counters, depending on if you want to use the TSC to find total execution time. So that allows you to use those counters for other stuff like power estimates and things like that.
Yeah, I'll be sure to send the manuscript to some of my contacts at Intel. Okay. Thanks, good talk.
Okay. Can I ask additional questions?
Oh, yeah.
So you just mentioned that the memory latency is the main aspect that affect processor performance. So do you consider the memory throughput into this? So sometimes when the memory access is too frequently, and the memory throughput upon the performance.
So that is one of the limitations of any of these memory time, core time systems, where, for instance, if you start running out of bandwidth, your memory latency, in fact, constant. So when you're out of bandwidth, the more accesses you put in, the longer every access takes. And that is a limitation of the theoretical models that we were trying to emulate here, and it's so therefore a limitation of what we have, where if you are, you would need to add extra things in to start dealing with memory bandwidth concerns. And that was also pointed out in Micro 2012 on a paper by Yale Pat's group.
Okay, thanks.